The Poynting theorem, the energy is transmitted from transmitter to the receiver. The rate of energy flow is known as the power density. The electric field is measured in volts per meters. The magnetic field H is measured in terms of ampere per meters. The product of these two is volt ampere per meter square or watts per meter square, power per unit area or power density. The dot product of E and H is a scalar quantity. The cross product of E and H is a vector quantity, so that the power radiated from an antenna flows in a particular direction. The cross product of E and H is the power density. Poynting theorem. The Poynting theorem can be defined as the rate of decrease of energy stored within the volume V minus the power dissipated. So that E is equal to Ex Ax, H is equal to Hy Ay. So that P is equal to E cross H is equal to Ex Ax cross Hy Ay. E is equal to Eh Ax cross Hy Az. The direction of power flow is in the z. The direction of power flow is in z directions. Ex is equal to Em cos of omega t minus beta z Ax. Hy is equal to Em upon eta cos of omega t minus beta z Ay. P is equal to Ex Hy Az, so that P is equal to Em square upon eta cos square of omega t minus beta z Az. The average power density can be determined by integrating the power density over one cycle and dividing by the total time period t. The average power density is 1 upon t is equal to 0 to t em square upon eta cos square of omega t minus beta z into dt. As the power density is equal to Em square upon t neta integral 0 to t 1 plus cos of 2 omega t minus beta z upon 2 into dt. Average power density is Em square upon t neta integral 0 to t into bracket of 1 by 2 plus cos of 2 omega t minus beta z upon 2 dt. Average power density is Em square upon t neta into bracket of t by 2 plus sin 2 omega t minus beta z upon 2 into 2 omega 0 to t. Average power density is Em square upon t neta into bracket of t upon 2 plus sin 2 of omega t minus beta z upon 4 omega minus sin of minus 2 beta z upon 4 omega square upon t neta into bracket of t by 2 plus sin of 4 pi minus 2 beta z upon 4 omega plus sin 2 beta z upon 4 omega. Em square upon t neta into bracket of t by 2 minus sin 2 beta z upon 4 omega plus sin 2 beta z upon 4 omega. So that average power density is Em square upon 2 neta. In free space, E is equal to 150 sin of omega t minus beta z Ax volt per meter. Calculate the total power passing through a rectangular area of sides 30 mm and 15 mm in z is equal to 0 plane. So that the Em upon Hm is equal to N0 and N0 is equal to 120 pi ohm. Ex is equal to Em sin of omega t minus beta z. E is equal to 150 sin omega t minus beta z Ax. So that the power radiated in a particular direction is average power is equal to Em square upon 2 newton naught. The P average is equal to average power density in volt ampere per meter square or watts per meter square. Average power density is 150 upon 2 into 120 pi is equal to 0.1989 watts per meter square. The power passing through a rectangular area is equal to 30 into 10 raised to minus 3 into 15 into 10 raised to minus 3, that is sides of the rectangular area is 15 into 10 raised to minus 3 is equal to 450 into 10 raised to minus 6 meter square. So that the power is equal to power that is the power passing through rectangular area is power density into area. 0.1989 into 450 is equal to 89.505 microwatts. That is the power which is passing through a rectangular area. Calculate the total power passing through a rectangular area of sides 30 mm and 15 mm in z is equal to 0 plane. In free space, E is equal to 50 cos of omega t minus beta z ax volt per meters. Find the average power crossing a circular area of radius. Find the in free space E is equal to 50 cos of omega t minus beta z ax volt per meters. Find the average power crossing a circular area of radius 2.5 meter in the plane z is equal to 0. Assume Em is equal to Hm n0 and n0 is equal to 120 pi ohms. E is equal to 50 cos 50 e raised to j into bracket of omega t minus beta z ax. H is equal to 50 upon eta naught e raised to j into bracket of omega t minus beta z into ay. Em is equal to 50, so that average power density is equal to Em square upon 2 eta naught 50 square upon 2 into 120 pi. Average power density is 0.066 watts per meter square. The average power crossing a circular area of radius 2.5 meter is area of circle is equal to pi r square. Pi into 2.5 whole square is equal to 19.63 meter square. So that power is equal to power density into area. 0.66 into 19.63 is equal to 1.29 watts. Polarization. The time-varying behavior of electric field vector along the direction of propagation is known as the polarization. The time-varying behavior of electric field vector along a direction of propagation is known as the polarizations. So types: linear polarization, elliptical polarization, circular polarization. The linear polarization. The electric field E along x direction is Ex, along y direction is Ey. In linear polarization, the two electric field vectors Ex and Ey are in phase and having a different magnitudes. And the Ex component reaches maximum or minimum, then Ey component also reaches maximum or the minimum value. When Ex component increases or decreases, the Ey component also increases or decreases. The electric field E is the resultant of Ex and Ey depends upon the magnitudes of Ex and Ey. Theta is equal to tan inverse of Ey by Ex. So that here the angle between electric field E and the x-axis. If the magnitudes of both Ex and Ey are equal, then theta is equal to 45 degree. The Ex and Ey component are in phase and having equal or unequal amplitudes. The wave is linearly polarized. That is, here the electric field E along x direction is Ex, along y direction is Ey. In linear polarizations, the two electric field vectors Ex and Ey are in phase and having different magnitudes. The two the two electric field vectors Ex and Ey are in phase and having different magnitudes. The two electric field vectors Ex and Ey are in phase. The two electric field vectors Ex and Ey are in phase and having different magnitudes. The Ex and Ey components are in phase and having equal or unequal amplitudes. The wave is the linearly polarized. Elliptical polarizations. The electric field components Ex and Ey are not in phase and are not having equal magnitudes. The components become maximum and minimum at different instants of time. The electric field vector E is the time variant if the locus of endpoints of E is traced, that results in a ellipse. The components Ex and Ey are not in phase and having unequal amplitudes. The ellipse is inclined at an angle theta with the coordinate axis. The components are not equal in amplitude, but the phase difference is exactly equal to 90 degree. Then the axis of the ellipse lies along the coordinate axis. That is, here the components Ex and Ey are not in phase and having unequal amplitudes. The ellipse is inclined at an angle theta with the coordinate axis. Here it is inclined at an angle with coordinate. The components are not equal in amplitude, but the phase difference is exactly equal to 90 degree. Then the axis of the ellipse is along the coordinate axis. If the components Ey is greater than Ex, phase difference is 90 degree, then the major axis of the ellipse lies along the y-axis. If the component Ex is greater than the Ey, phase difference is 90 degree. Then major axis of ellipse lies along x-axis. That is, here this one, it is the major axis, and here it is the minor axis. So that if the component Ex is greater than Ey, phase difference is exactly equal to 90 degree. Then major axis of ellipse lies along the x-axis. If the component Ex is greater than Ey, phase difference is 90 degree, then lies along x-axis. If the component Ey is greater than Ex, then major axis of ellipse lies along the y-axis. Circular polarization. The components Ex and Ey of electric field vector E are having unequal amplitudes, and the phase difference is exactly equal to 90 degree. The component Ex becomes maximum, other component equal to 0. The one of the component increases or decreases, the other component decreases or increases. The resultant vector E varies with time. The locus of endpoints of E is traced along the direction of propagation that results in a circle. This type of polarization is known as the circular polarization. E is equal to Ex cos of omega t minus beta z Ax, Ey cos of omega t minus plus beta z volt per meters, where delta is the phase difference between Ex and Ey. Omega t minus beta z plus delta. So that the electric field vector E is equal to Ex cos of omega t minus beta z omega t minus beta z plus Ey cos of omega t minus beta z plus delta. If z is equal to 0, then E is equal to Ex cos omega t plus Ey cos of omega t plus delta. Delta is equal to pi by 2, so that phase difference is exactly equal to the 90 degree. So if omega t is equal to 0, Ex is equal to 0, Ey is equal to plus Ey, and omega t is equal to pi by 2, Ex is equal to plus Ex, Ey is equal to 0. Omega t is equal to pi, Ex is equal to 0, Ey is equal to minus Ey. Omega t is equal to 3 pi by 2. Modulus of Ex is equal to minus Ex, and modulus of Ey is equal to 0. The locus of the end points of E is traced, that results in a circles. Propagation of uniform plane wave in good conductors. A good conductor is a material having high conductivity of the order of 10 raised to 5 moves per meter or Siemens per meters. Sigma is greater than 1, so that sigma upon omega epsilon is greater than 1. That is sigma greater than omega epsilon. In the equation for the propagation constant of the wave, propagation constant of the wave, gamma is equal to square root of j omega mu into bracket of sigma plus j omega epsilon. Sigma is greater than j omega epsilon. Gamma is equal to square root of j omega mu sigma. Gamma is equal to square root of omega mu sigma square root of j. J is equal to 1 angle 90 degree. Square root of j is equal to 1 angle 45 degree is equal to square root of omega mu sigma into bracket of 1 angle 45 degree. So omega mu sigma into bracket of cos 45 degree plus j sin 45 degree. J 1 by root 2. Gamma is equal to square root of pi of mu sigma plus j square root of pi of mu sigma. Gamma is equal to alpha plus j beta. Gamma is equal to propagation constant, alpha is equal to attenuation constant, beta is equal to phase constant, and alpha is square root of pi of mu sigma. Attenuation constant and phase constant are directly proportional to the square root of frequency and conductivity for a good conductor. The intrinsic impedance is square root of j omega mu upon sigma plus j omega epsilon. Sigma is greater than j omega epsilon. Square root of j omega mu upon sigma, omega mu upon sigma square root of j 1 angle 90 degree, square root of omega mu upon sigma 1 angle 45 degree is equal to pi of mu upon sigma. The electric field vector Ex propagates along z directions. The attenuation and phase constant are considered. Then Ex is equal to m raised to minus alpha z into e raised to minus j beta z. The amplitude of the wave propagating in a good conductor is maximum at z is equal to 0, and is equal to em. The amplitude of the wave goes on decreases as the distance increases. That is em e raised to minus alpha z. At z is equal to delta, that is amplitude is em e raised to minus alpha delta. If delta is equal to 1 upon alpha, then the amplitude of the wave is em e raised to minus alpha upon alpha is equal to em e raised to minus 1. That is 0.368 em. Delta is equal to skin depth or depth of penetration, the distance through which the amplitude of the wave propagating in a good conductor decreases to 37% of its maximum value is known as skin depth or depth of penetration. The currents and fields are confined to a thin layer near the surface of a conductor. This thin layer is nothing but the skin of the conductor. Hence, the effect is known as skin effect. The external interference, and here it is the coaxial cables. In coaxial cable, the inner conductor carries the signal. The outer conductor is made up of a material having a properties of good conductors. Any external interference at the outer conductor, the magnitude of it decreases at the certain distance. The input signal is not interfered by the external interference. The parameters in terms of skin depth are the attenuation constant alpha is equal to 1 upon delta is equal to square root of pi of mu sigma. Phase constant beta is equal to 1 upon delta is equal to square root of pi of mu sigma. And gamma is equal to alpha plus j beta is equal to 1 upon delta plus j upon 1 upon delta propagation constant. Intrinsic impedance is neta is equal to 1 plus j1 into bracket of square root of pi of mu upon sigma root of sigma upon square root of sigma. Here it is equal to square root of pi of mu sigma upon sigma into 1 plus j1. So that here neta is equal to 1 upon sigma. Here it is the delta 1 plus j1. Velocity is equal to v is equal to omega upon beta is equal to omega delta, and wavelength lambda is equal to 2 pi upon beta is equal to 2 pi into delta. A uniform plane wave is traveling at a velocity of 2.5 into 10 raised to 5 meter per second, having wavelength lambda is equal to 0.25 mm. In a non-magnetic good conductor, calculate the frequency of wave and the conductivity of a medium. The velocity v is equal to f lambda, f is equal to v upon lambda, v is equal to 2.5 into 10 raised to 5 meter per second, lambda is equal to 0.25 mm is equal to f is equal to 1 gigahertz. Conductivity of a medium is equal to v upon omega upon beta, but for good conductor, phase constant is given by beta is equal to square root of pi of mu sigma. Beta is equal to omega upon v is equal to 2 pi f upon 2.5 into 10 raised to 5 is equal to 5 into 10 raised to 5. Beta is equal to 2.5 into 10 raised to 4 radians per meters. Beta is equal to square root of pi of mu sigma. For non-magnetic material, mu r is equal to 1, so that mu is equal to mu naught mu r is equal to 1. So that here beta is equal to square root of pi of mu sigma. From that one is write the shall calculate the conductivity of the medium is equal to 0.15 into 10 raised to 158 into 10 raised to 6 mega Siemens per second. The wet marshy soil is characterized by sigma is equal to 10 raised to minus 2 Siemens per meters, epsilon r is equal to 15, and mu r is equal to 1, so that at 60 Hz it can be considered as a good conductor. Hence, at 60 Hz calculate the skin depth, intrinsic impedance, and the propagation constant of the that is the parameters. Here at 60 Hz the condition for the given material to be a good conductor is sigma upon omega epsilon greater than 1. 10 raised to minus 2 upon 2 pi into 60 into 8.854 into 10 raised to minus 12 into 15 greater than 1. So that from that one 2 into 10 raised to 5 greater than 1, the ratio is large as compared to unity. The ratio is large as compared to unity. The given wet marshy soil is a good conductor at 60 Hz. The given wet marshy soil is a good conductor at 60 Hz. So that the skin depth delta is equal to 1 upon alpha is equal to 1 upon square root of pi of mu sigma. Delta is equal to 1 upon square root of pi f mu sigma is equal to 6.45 10 raised to 2, and neta is equal to 1 upon sigma delta plus j 1 upon sigma delta is the intrinsic impedance neta is equal to 1 upon sigma delta plus j 1 upon sigma. Propagation constant is gamma is equal to alpha plus j beta is equal to 1 upon delta plus j 1 upon delta is equal to a 800 megahertz plane wave traveling has an average Poynting vector of 8 milliwatt per meter square. If the medium is a lossless with mu r is equal to 1.5 and epsilon r is equal to 6, find velocity of wavelength, impedance of the medium's RMS electric field and the RMS magnetic field. The medium is a lossless medium. For lossless medium, sigma is equal to 0, mu r is equal to 1, epsilon r is equal to 6. Velocity is v is equal to 1 upon square root of mu epsilon is equal to 1 upon square root of mu naught mu r epsilon naught epsilon r. From that one v is equal to 1 upon 4.10 raised to minus 7, 1.5 into 8.854 into 10 raised to minus 12 into 6 is equal to 1 into 10 raised to 8 meter per seconds. Lambda is v upon f is equal to 1 into 10 raised to 8 upon 800 into 10 raised to 6.125 meters. And intrinsic impedance is square root of mu upon epsilon mu r upon epsilon naught epsilon r is equal to neta is equal to 4.10 raised to minus 7 into 1.5 upon 54 into 10 raised to minus 12 into 6, 188 ohms. The average power density or Poynting vector is 1 upon 2 em square upon neta 8 into 10 raised to minus 3 upon is equal to em square into 8 into 10 raised to minus 3 into 188 into 2 is equal to 17.34. em is equal to 17.34 volts per meters. RMS electric field E is given by em is equal to square root of 2 into ERMS. ERMS is equal to em upon root 2. ERMS is equal to 12.26 volts per meters. And the intrinsic impedance is ERMS upon HRMS is equal to ERMS upon neta is equal to 12.26 upon 188 is equal to 0.065 ampere per meters.